as you can see, this is the original model. Variance of the beta 1 hat, it will be formed with this one. And then variance of the, this is the reason is this is the, because we have only simple regression, so you can take it out this one. So what you can tell is always this is a certain number, right? So in denominator. So if you take it out, but r square cannot be greater than 1, so this will be the so I will write down again here. Versus no, here I will write this one, square versus and nothing, right? So since this value 1 minus r square should be less than 1 and greater than 1, so this is like a 0.5 or something like that. So if you have a something in denominator that is less than 1, actually this one makes this one bigger, right? Because you are dividing certain number less than 1, so the total number is getting bigger. So always this is bigger. So if you omit one variable, you may increase the bias, but actually you can reduce the variance, right? So if beta 2 was 0, right? So beta 2 was 0, so which means if this is a 0, then or even in original model, we can just get rid of this one. Then what we can do is, since we're taking out, your variance is getting smaller, right? And then expected of this value will be still the beta 1 because this was 0. Do you remember the new beta 1 was the beta 2 times, right? This formula. We thought that if it's uncorrelated, this is 0, but that's the other case. This is the case, beta 2 is 0, then this is a 0, then this will be 0, and our expectation is still same. So we can get rid of the bias. Even though I taking out the variable, we don't generate any bias because the variable we get rid of them seems like irrelevant. So simply we don't add the bias, and then we just reduce the variance here. Therefore, this might be the case we want to get rid of them. But this is a simple because the beta 0, beta 2 is a 0, so why do I have to have that variable? But beta 2 is not 0, that case, we will have a bias, but still the variance will be the smaller, right? So this is kind of trade-off. If you really want to reduce the variance, I can have a little bit of bias, that's fine, but I want to really reduce the variance, then you can drop some independent variable, right? But remember, this bias will not be reduced even you use a lot of sample. However, this variance can be reduced by using large sample. If you can collect a lot of data, you can reduce this data. However, the bias is not, it will not be gone even though you use a lot of sample. So that's why the most of case people trying to not to drop important factor, because if you want to make your regression more correct, you can just simply collect the more sample. However, bias will not be reduced. But very special case, if you allow a little bit of bias, but I want to really reduce the variance, then you can drop some factors. That's the trade-off between bias and variance. Okay, this is the error variance. Estimating the error variance is this is, you can consider this is similar to the like a sample standard deviation, which is the S equals sigma over x, right? Minus x bar square divided by n minus 1. Here 1 was because I use a estimate one variable. But here why this is the k minus 1, because we use a k minus 1 factor to calculate this u hat. U hat is the y minus y hat, and then y minus beta 0, right, plus beta 1 x1 plus beta k xk. So I use a k parameter and then one more. So that's why we are subtracting n minus k plus 1, because to calculate the u hat, I estimated what k plus 1 number of a variable. That's why we have to divide, instead of n minus 1, we have to divide by n minus k minus 1. This is actually the degree of freedom. Okay, so theorem, if we have all 5 assumption we previously have, this estimator using this degree of divide by degree of freedom will be the unbiased estimator, just like this is the unbiased estimator in the sample standard deviation. This will be the unbiased estimator for the error variance. So estimate of a sampling variance. This is a sampling variance. So this is standard deviation of this coefficient will be the variance, square root of the variance. So this SD is a standard deviation. And then we already know this formula, so we can just plug in. But here, this is the sampling standard error of this one will be this way, and then you should choose this one with the estimated one, because this is the true sigma, but we don't know the true sigma, so you have to use our estimator, and then the same way. But what we call is different. This is a standard deviation, that what is supposed to be, but problem is we don't know this sigma square, so we have to use our sample sigma square. So this formula is only valid under the assumption, all assumption we already have in the first 5 of assumption. Especially there should be no heteroskedasticity, which is the variance of the u given x should be sigma square. So it will not change by x. Variance will not change. Efficiency of the OLS is they say it's a Gauss-Markovian theorem. Actually, this is just a simple explanation. You don't have to. I don't think it's important here. If under the assumption this OLS is unbiased, however, we want to have a smallest variance, right? So unbiased and then smallest variance. So the bias and the variance is trade-off. So can I get an unbiased estimator but the smallest variance? So that by theorem, what we can say is if this all assumptions hold, These OLS, ordinary least square estimators, are the best linear unbiased estimator that we call is blue. The best linear unbiased estimator. This is the best one. Smallest variance and unbiased estimator. If all 5 assumptions holds. Okay. So OLS is only the best estimator only if this holds. If there is some other problem, then there can be a better estimator. But that's why we use OLS basically.